Hey students, no, it's not your imagination. There really is a warm-up to start day 4 of the factoring unit. So pause the video now and do a little factoring. When you're done with the warm-up, you can tune back in and we'll be talking about choosing a factoring method today. Okay, so how did it go? Are you getting really good at this AC factoring method? Well, I hope your answer is yes. Because as we move into the final day of our factoring unit, we're going to be doing a lot of mixing in the different methods that we've used for factoring. We've done greatest common factoring, we've done common binomial factoring, we've used the AC method, and in this most recent lesson we learned about some special cases, the perfect square trinomial and the difference of squares factoring pattern. So we're going to kind of be mixing them all in, and we're going to be testing our skills at choosing a factoring method, since we've got a lot of different methods that we've learned. So our learning goals, we have 2 of them. The first one is to choose an appropriate method for factoring a polynomial. And secondly, to combine methods for factoring a polynomial. Now notice that the learning goals are 8.6.1 and 8.6.2. Now the reason why they say 8 is it's not Chapter 8 of Algebra 2, it's actually Chapter 8 of Algebra 1. Because as I've been saying throughout this unit, it is a review of factoring. So if a lot of these things seem very familiar up to now, they really should, because this is something that we do in Algebra 1. And this is just kind of, we're going to reach back into Algebra 1 and reviewing that, so as we move into our next chapter on quadratics, where we've just got a real handle on this skill of factoring, because it's a really necessary skill. So let's take a look at this table of listing some different factoring methods. So factoring methods. Let's take a look at the first row of this table, which is factoring out the GCF. So what a problem might look like is listed here: 4x cubed plus 6x squared plus 8x. And notice that there is a common factor in all 3 terms. And when you have something like that, when you have something in common in all the terms, we do GCF factoring, where we find the greatest common factor of the coefficients and of the variables, if any, and we factor that out. So this is what that might look like. So take a moment and see if you can identify the greatest common factor and factor it out, and I will as well. So I recognize that the greatest common factor was 2x of all the terms, and I went ahead and factored it out. And notice that there are 3 terms in the answer and a piece out in front. So this is characteristic of what the result of a greatest common factoring process would look like. Factoring by grouping. So factoring by grouping, notice that there are 4 terms. So when we had 4 terms, remember what we did with that? We split them up 2 and 2, and we factored out the GCF and recognized a common binomial, and we're then able to figure out the 2 binomials that would multiply to give us the original polynomial. So this is what it looked like. We would take and we would split the 4 terms up 2 and 2. We would take out the greatest common factor of the first 2, which in this case appears to be 2x, which would leave me with x minus 1. And in the second 2, it looks like it is a 3, positive 3, which leaves me with 2x minus 1. Oops, and this was supposed to be, I hope you caught that, keep me on my toes, 2x minus 1. And that's actually a good thing to happen, because, you know, if you do something like this, factor by grouping, and your binomials don't match up, you don't have a common binomial, you must have done something wrong, or it's not factorable. So I realized I did something wrong. So anyway, when I took out the, and when I rewrote it, I made another error. I'm just having one of those days. So that was supposed to say 2x. And so I know that what that factored form would look like then is it would be the common binomial, so the one that you saw repeated, and then the numbers that are out in front of those 2 monomial terms create a binomial together, And that's my factored form. And notice that there are two binomials. So factor by grouping will produce us our two binomial factors. And then factoring a polynomial in its entirety. So taking it from its original form and doing whatever it takes to actually be able to break it down into two smaller binomials. And this is where we use the AC method. So notice that this polynomial, 2x squared plus 13x plus 11, notice there's three terms, and the first one is squared. And so when we were doing something like this, we used the AC method, and this would look like the following. I would multiply the A and the C. They multiplied together to give me 22. I look for factors of 22 that add to 13. In this case, it would be 11 and 2. I split the middle term up. I keep the first and last terms the same. All right, one of them first, 2x, and then 11x, because then 2x plus 11x make that middle term 13x. So the first and the last term stay the same, and then I split the four terms up and factor by grouping and take out the common factor of the first two and the common factor of the second two, and get my final two binomials, which is called the final factored form. It would be 2x plus 11 and x plus 1. So notice here that there are two binomials as well. So what we want to be able to do is to be just presented with the problem, and it could be, any of these three types in that center column of our table, or even something different. It could be one of those special factoring patterns or whatever. And we want to be comfortable with recognizing whatever kind of problem it is and what the strategy is we'll have to use to factor it. Okay? So, well, first of all, we have to be able to determine if a polynomial is fully factored or not, because if it is, then we have no work to do for that. So basically what we want to be able to do is look to see if there's any way to break down any of if it looks like it's in sort of a factored form, see if we can break it down any further. And if it's not, then see if we can actually factor it. So that's what example 1 asks us to do, is to determine whether a polynomial is completely factored or not. Well, if you take a look at example A, it says 3x squared times 6x minus 4. Well, if you, there's no way you can break down the monomial anymore, 3x squared. You can't do anything with that. But if you take a look at the binomial here in the parentheses, there actually is a common factor to the 6 and the 4. And so basically it looks like when somebody factored whatever the original polynomial was for the GCF, they just didn't get a big enough number out. So we actually could go ahead and take out of this piece, we could take out a 2 out of the 6x, and that leaves me with 3x, and a 2 out of the 4, that leaves me with minus 2. And so we could actually break this down further, which if I did that, then the two numbers on the outside would multiply to give me 6x squared, and then times 3x minus 2. So that was not completely factored, and so I'd say no, it's not completely factored, and I went ahead and factored it down further, and that is my final answer. Now it looks like example B, it has been factored into two binomials, so then the question is going to be, are the two binomials in their lowest form? Could they be broken down any further? And so when I look at this first binomial, x squared plus 1, you might be thinking about that whole difference of square things because, x squared is a perfect squared and so is 1, but it's not a difference of squares. The only factor pattern that involves two perfect squares is one that's called the difference of squares. And so this is a sum of squares. So there's nothing I can do with that. So that's all set. That part's no. Then I look at the other binomial. Can't break it down any further. And so we'd have to say this one is fully factored, and there's nothing more that we can do to it. Okay, so let's turn the page. Here are a couple for you to try. So these are you try questions. Take a look at each example and see if you can break them down any further. If so, then go ahead and do that, and if not, say it's fully factored. Pause the video now. All right, so we had one that was fully factored. There was nothing more I could do there. And one that still had a little work to be done on it. That first binomial, 4x plus 4, those two terms had a greatest common factor of 4. And so I went ahead and factored that out. And then I saw something else. I saw that the two binomials that were left over, the x plus 1 and the x plus 1, were the same. And so I went ahead and rewrote that as x plus 1 squared. So a final factored form of 4 times x plus 1 quantity squared. So to factor a polynomial completely, you may need to use more than one factoring method. So you may need to use more than one factoring method. Use the steps below to factor a polynomial completely. So our first step will be to factor out a GCF. So we always want to see if there's possibly a greatest common factor that we can take out. Maybe we even want to factor out a negative if the leading coefficient is negative, and I showed that in a prior lesson as well. But that still would be a greatest common factor. And so that would be step one. Step two would be to use the number of terms to decide on a factoring method. So for instance, if I had something that was 3 terms, I might think, oh, I've got to use the AC method and try to actually break that middle term down into 2 separate terms so that I had 4 terms. Then I could use factor by grouping. Or if it already was 4 terms, then I would want to maybe start off with factor by grouping once I took out a GCF. Or maybe it's just 2 terms, and I might think, oh, look at, that's 2-term polynomial, and it's a subtraction between the terms. Maybe the first and last, those 2 terms are perfect squares. If so, it might be a special pattern. Or maybe I have a perfect square trinomial. So, you want to examine, kind of analyze what you have and see if you can choose on a factoring method. Once you've chosen a factor method, then go ahead and factor all using the appropriate method. And then check all the elements of the answer to see if any parts can be factored further. So you might get down to the point where you have 2 binomials, but maybe one of the binomials could be factored further, as was in the case in example D up on the top of this page. And finally, check your answer by multiplying it back out and comparing it with the original problem. So using your FOIL or distributive property or whatever to check back and see if it matches up with the original problem. So let's work through these 5 steps with example 2. So it says factor 10x squared plus 48x plus 32 completely and check your answer. So step 1, factor out the GCF. So I'm going to take a look at these terms and see if there's a greatest common factor that I can take out of each one of those terms. And I can see that, they're all even numbers. So I know for sure I can at least take a 2 out. So I'm going to go ahead and do that. I'm going to factor out a 2. And they don't all have an x or a variable, so I can't really do anything with that. But I'm going to go ahead and take out the 2. And that leaves me with 5x squared plus 24x plus 16. And now I look again, 5, 24, and 16. Nope, there's no common factor for those. So I must have gotten the largest number when I factored out the 2. And now I'm going to go ahead and take a look at what's inside my parentheses. And I'm going to see if I can break that down further. But I always have to keep in mind that there's this little 2 out here that I know has to be part of my final product. But when I look inside the parentheses, I see that it's a 3-term polynomial. The first and last terms are not perfect squares, so I know it's not going to be one of those special patterns, but I could use the AC method. So that's what I'm going to do. I'm going to go ahead and see what 5 times 16 is, and it's 80. And then I think about factors of 80, and I'm trying to get them to add up to 24 so that I can split that middle term up. And I'm thinking of 20 and 4. And they multiply to 80, and they add to 24, so that would work. So I keep my first and my last terms exactly the same, and I go ahead and split that middle term into a 20x and a 4x, and again, either one can come first. Okay, and now I take those 4 terms, because once I have a 4-term polynomial, I think factor by grouping. So now I'm going to go ahead and separate out into 2 smaller groups and take out the common factor. keeping in mind that I'm bringing that 2 down all along. So I could take out a 5 and an x out of the first two, and that leaves me with an x plus 4. And then out of the second grouping, I can take a positive 4 out, which leaves me with an x plus 4. So of course there's my common binomial factor. And so writing my final answer would look like this. I'd have my 2 out in front that I had originally factored out, my GCF. Then I take my 2 numbers that were out in front, my 2 monomials, and they create together a binomial factor of 5x plus 4, and then the common binomial, which was x plus 4. And there's my final answer. And I know by looking back at those binomials, 5x plus 4 and x plus 4, there is no more that I can do to either of those because there's no greatest common factor of 5x and 4 or x and 4. So that is my final factored form. That's fully factored. That's a lot of f's. So let's go ahead and turn the page. And of course we have a you try problem, so I want you to try example B. Pause the video and try it, and then tune back in to check to see how you did. Okay, so this one was an interesting question because I noticed right away that there was a common factor for the numbers 4, 16, and 16. And so I knew that the common factor of 4, 16, and 16 was 4. And of course, each term had at least one x to give. So I was able to factor out a 4x. Now right away I didn't recognize that the remaining trinomial, x squared plus 4x plus 4, was a perfect square trinomial. Now if I had, I could have gone straight to my final answer over here. Because I see I have a perfect square in x squared that starts it off. It ends with a perfect square of 4. I know that when I take the square root of the first and the last and multiply them and double it, that's will give me that middle term of 4x. So that's the check to see if you have a perfect square trinomial. But I didn't see it. And that's okay. I didn't see that right away, so I went ahead and did the factor by grouping method, the AC method, by splitting up that middle term as 2x and 2x. And so it took a little more work, but I was still able to get the final answer of 4x times x plus 2 squared. Now what if you tried and you went through that whole entire table, you thought about all the different factoring methods that we've learned, and you can't come up with anything? Well, that just means that the polynomial is unfactorable. You just say it's not able to be factorable, it's unfactorable. And a real red flag for that is if you're using the AC method and you multiply the A and the C and you cannot find factors of the product of A and C that add up to the middle term B, you can pretty much be assured that if that's the case and you've thought about all the factors of the product of A and C and you can't get that middle term B, that it's not a factorable polynomial. Let's take a look at these examples and see if maybe we can identify any of them that are unfactorable. Well, example A, I would think right away I'm going to have to try that AC method. So I multiply the A and the C, the 12 and the negative 1. And I get negative 12. And I'm thinking of factors of negative 12, which means one of them has to be positive, one has to be negative, and they have to add up to a positive 1. And I can think of one right away. I mean, I can think of 4 and negative 3. You know, they multiply to give me that negative 12 and they add to give me a positive 1. So this is going to be factorable. This is something I can do. I should be able to do that. This is factorable. And I could go ahead through that AC process and factor it. Now, example B, if I multiply the A and the C, I have 5 times 9, which is 45. And I think about factors of positive 45, meaning they have to either both be positive or both be negative. And they have to add up to negative 3. That means they're going to have to both be negative. And there is no way I'm going to get factors of 45 that are going to add up to a negative 3. The factors are just going to be too large. In fact, I think the smallest factors are 9 and 5. So if they were both negative, the smallest number they could add up to, the -9 and -5, would be -14. Well, not small. Well, that would be the closest it would get to -3. So this one's not factorable. How about C? Well, I've got 2 and 7, and they multiply to give me 14. And I think about factors of 14, and they have to add up to -9, and I can think of them right away. -7 and -2. They'll add up to the -9 that I need them to. So this one is factorable. And again, I could kind of go through that process of the AC, and I could actually factor and find the two binomial factors of that. So let's go ahead and try example 3, which is factoring by multiple methods. So example A, 9x squared plus 3x minus 2. I see right away that it's 3 terms. I don't see a GCF that I can take out, so I'm going to go ahead and look at the AC method and see if I can take my A and my C and multiply them. 9 times -2 is -18. So I'm thinking right away I have to have things with two different signs, one positive, one negative, and they're going to have to add up to a +3. So I'm thinking, how about +6 and -3? Well, those multiply to give -8 and they add to give +3. So that looks like that will work. So I'm going to go ahead and rewrite the polynomial as 4 terms. So I do that by keeping the first and the last terms the same, splitting the middle up into 6x and -3x. And again, it doesn't matter which one comes first. So actually, I think I'm going to, we'll go 6x first, and then -3x. And I'm going to split them up and look for GCF. Well, the first pair, the GCF I can see is probably going to be a 3 for the 9 and the 6, and then of course they both have at least an x to give. So when I factor out the 3x out of 9x squared, I get 3x, and out of the 6 I get 2. Now looking at the -3x minus 2, well, first of all, immediately I think it's the leading coefficient is a negative, so I want to at least take out a negative. But then 3 and 2, they don't have any common factors, and there's no variables, but you got to be able to take out something. So if you can't take out anything, you should at least factor out a 1. And in this case, I can actually factor out a -1. So I specifically chose to write it like this so that I could bring this up. So if I take out a -1, and that's going to make the -3x actually equal to +3x, and the -2 equal to a +2. And now I was able to get it so that my binomials are the same, and that's going to give me a final answer of 3x minus 1 times 3x plus 2. I couldn't fit that on the page, so sorry, they're not right next to each other. But that is the final answer right there. Now, I really didn't have to use another factoring method here, so sometimes you do, sometimes you don't. In this particular case, I got down to my 2 binomials, and they were really as factors as I could get them. When I look at example B, though, now immediately I see I'm going to be able to do a GCF method. These all have coefficients that are divisible by 12, so immediately I thought, well, I'm going to take out a greatest common factor, and I know I can at least take out a 12. They all have at least 1b, so one has b cubed, 1b squared, and 1b, so I could take out a b. So I'm going to factor that out, and that's going to leave me with b squared plus 4b plus 4. And then I think, oh, hey, I want to check to see if that's a perfect square trinomial, because I know when I look at that first term, this first term is a perfect square. The last term is a perfect square, and remember how I check that? I look to see if I take the square root of the first term, the square root of the last term, so the square of the first term was b, the square root of the last term was 2. If I multiply 2 and b, I get 2b, and if I double it, I get 4b, which is that middle term. So I know this is one of those perfect square trinomials, and if I hadn't recognized that, I could have gone ahead and used the AC method and broke it down that way. But still, I'm using more than one factoring method. I'm using GCF, and this time I'm using a perfect square trinomial pattern. Now, you may have not noticed that if you were doing this independently, and you might have done the AC. That's okay too. We're all going to get to the same place at the same time with just different methods. So I have that 12b out in front, and now I can break this down into two identical binomials, because that's the pattern, perfect square trinomial pattern, and they are b plus 2, both of them. Which means I could then write this as 12b times b plus 2 squared. So let's go ahead and do one more together. So take a look at example C. That's not usually how we see polynomials presented to us. We usually see them in that descending order of powers. So as I mentioned in an earlier video, it's always a good idea to go ahead and rewrite that polynomial in descending order of powers first. So I'm going to do that, and it would look like this: negative 20 x cubed minus 28 x squared plus 5x plus 7. Now I don't see a greatest common factor that I can take out. You know, negative 20, negative 28, 5, and 7 it doesn't dawn on me that there's something common to all those. So I do see 4 terms though, so I'm going to go ahead and split these up, and I'm going to try to do factor by grouping. So when I look at the first two, I see that I could take out, and I always try to take out a negative if possible. So I'm going to go ahead and take out a negative 4. It looks like I can take a negative 4 and an x squared out. That's going to leave me with 5x and then plus 7. And now when I come to the 5x plus 7, the other pairing, there's nothing I can take out. And so remember what I said before, if there's nothing you can take out, you should always take out a 1. And so I did that. And now that means my two binomials would be negative 4x squared plus 1 and 5x plus 7. And actually, this negative 4x squared plus 1, if I factored out a negative, and I just rewrote this, took out a negative 1 because I don't like my leading coefficients to be negative, it actually would look like this. It would be negative 4x squared minus 1. And now hopefully you recognize that this is a difference of squares pattern. So I can break this down even further, and I already I'm running out of space, but if I do that, then it becomes two almost identical binomials. They just differ by sign, and they both would be 2x and 1 would be the term, so one would be 2x minus 1, one would be 2x plus 1, and of course we also have that 5x plus 7. And so we took and broke down the difference of squares to get that, and there's our final factored form. So sometimes these can get pretty in-depth, and we'll have to use multiple different factoring methods all in the same one. I took out I had to rewrite the polynomial, I factored by grouping, and then I saw a special factoring pattern. So you want to be diligent. You want to look at all of as you're along the way, look to see if there's any way you can break down any more binomials or other terms further so that you get your most fully factored form. Now, if you turn the next page with me, so what we're going to do with this page is we're going to plan to do these as you try problems in class. So we're going to wait until we meet in class again, and we'll take some time working through these problems. So start the hour just so we can, see if there's, any struggles that you're still having, or, you just need a quick review of going through all the factoring methods. So we're going to end it here, and this actually concludes our unit on factoring. So I'll see you in class.